Hey guys, we are going to continue with energy by doing worksheet 3, which actually brings in numbers. So at this point, we've done like 90% of the work on energy problems, but this time we're actually going to see how, changing the numbers, what actually happens with this stuff. For AP Physics, they really focus on these proportional reasoning relationships, and we'll start with number one. So number one asks, you have two balls, A and B, that are held 1 meter above the ground. A has a mass that is twice that of B. They're released and allowed to fall, which is going to be traveling faster when they hit the ground. Now, and my recommendation, all these worksheets, you should try to do them first, and then you can see what my reason and logic is going through it. But so basically all that's different is A is more massive than B. A has double the mass as B. But we already know from projectile motion that they're going to hit the ground at the same time. But we need to justify this with energy. The way I'm going to show y'all is, let's think of pie charts. And let's say at the very top, while you're holding it, it's all UG. You drop it right before it hits the ground. It's so close. I'm going to say there's no UG. So it's UG is equal to K. Now, for A, that would be 2m times g times h is equal to 1/2 2m v squared. Now, notice the 2m's cancel, and you're left with v is equal to square root 2gh. And you notice here, okay, my velocity does not rely on mass. It only really relies on g and h. And this is an equation that we could have come up with similarly with something like this in projectile motion or another kinematic equation. Notice that none of the kinematic equations have mass, so once you know the launch velocity and you know the height, you pretty much know how that object's going to travel. You can try this again with B and you'll probably get the same result. Let's try now. Ball B is held 2 meters above the ground. So ball B is 2 meters above ground, 2 times g times h. That would be square root 2 times 10 times 2. And I get square root 40. VA would be the same thing, except I'm 1 meter above the ground. I get square root 20. Now most people say, oh, you just multiplied this by 2, but it's actually square root 2. If you actually plug in the numbers, you'll get 6.32 meters per second for V sub B, and you'll get 4.47 meters per second, which is that increase by square root 2. Why is it that? It's kind of me going back to this whole thing where time is squared here. There's a parabolic relationship between time and how far you travel when you're accelerating, and that's what's happening here. You double the height, you're not actually doubling the time, so you're not doubling the velocity. And that's a relationship they will always ask in AP Classroom. Let's look at this binder on the table. And for this, they ask you, what is it relative to the table? So U sub g is equal to mgh. Well, the mass is 3, g is 10. H is the distance between the binder and the table. Well, here it's 0, and you're left with 0 joules. Joules are the units for energy. First time we're actually looking at it, so it's capital J. There's a lot of ways to write J, but essentially it is like what a lot of times is represented as a Newton meter, but there's a lot of ways it can pop up between, like this equation would be kilogram meters per second squared times meter. So there's a couple ways it pops up, just as long as you understand all energy is joules along with work. Work is also joules since it's energy transfer. All right, U sub g here is equal to mgh as well, so 3 times 10 times 0.68, that's how high we are above the ground. We get 20.4 joules. Now the last one asks, what about the energy change needed for the book between the book and the ceiling 2.5 meters above it? And I'll give you a second to try this out and see what you'll get. Hopefully y'all pause the video, see what you get. I'm going to show you my work. UG is equal to mgh, so that's 3 times 10 times negative 2.5. Oh, why is it negative? Negative 75 joules. The way I like to describe this is we've got this binder here, and compared to the table, I try to get energy out of it with regards to the table. I'm not going to get any because it's no height above the table, but above the floor, okay, if I knock it off, I can access that 20.4 joules of energy. If I want to raise this binder up, I don't have enough energy. If I try to knock it off, it's not going to float up to the ceiling. So what do I have to do? I have to put in 75 joules. So I like to think of it as I am missing 75 joules of energy for this binder to be up on the ceiling. I'm going to keep going. I try to keep these videos shorter so it's not as hard to upload. The next one is this bungee cord. This bungee cord's U sub S is equal to 1/2 kx squared. And these formulas, UG, US, and K, these are just, they're given to you on the formula sheet, but they're the big three that pop up for energy. So K is your spring constant, 140. X is your spring displacement, so 25 squared. If you plug that in, you will get, let me double check my math here, 43,750 joules. This question, we get K is equal to 1/2 mv squared. 1/2 0.05 v squared is equal to 40. If you do your math correctly, you will get V is equal to square root 1600 or 40 meters per second. Always reduce your radicals, by the way. In reduce radicals, reduce fractions in physics. We like to see the decimals. This one, I'll work it out, but there's a lot of conversions here, so if you don't understand it, it's all right. You always want newtons in meters, so that's basically what I'm converting here. They give you the spring constant in a very weird format, but this is what it would look like. You'd be left with this. All right, now number 7. At this point, you should be able to do these bar graph problems pretty effectively. I'm going to pause the video again, and I'm going to hope that you guys can at least set up through A through B, and then I'll show you how I would solve part C. And just to walk through my thought process on these problems, I see the cart's moving, so kinetic. There's no change in height, so no change in EG. There's no spring at first. In my system, I had to make it. It's a cart, spring, and floor. I could add the earth. It won't change anything. That's pretty much the only other thing I could think of adding. For position B, we have no movement. It's stuck on the spring, so there's a spring that's EE. And there's nothing about friction, or they actually say no friction, so that is no E-dis, essentially. E-dis would be friction. To solve for this stuff, if you ever set this up, you can always say 1/2 mv squared is equal to, oh, I put EG here. This is EE. It's equal to 1/2 kx squared. This is like always a first step you'll do. EK is equal to E. This is called the quantitative energy conservation equation. Then you substitute. Then you just start plugging in the numbers you're given to try to solve for this. We're trying to go for maximum compression of the spring. That's going to be essentially your X. Remember, X is how much you've changed. K is your spring constant. 1/2 will cancel. I'll be left with X squared is equal to mv squared over K, or X is equal to the square root of M. They give us over here at the top here all these values, 8 times 5 squared over 50. And if you do this correctly, 25, 204, you get 2 meters as your answer. All right, how about y'all try this next one? I think this would be good practice, and if you do it, you should be feeling pretty good. All right, here's my answer for this problem here. The one thing I could see people kind of not realizing is the mass here is 500 grams. 500 grams is equal to 0.5 kilograms, so that's why I placed it here in the MGH part of this equation. All right. Let's go down to number 9, and we don't have too much, and I'll probably stop this one. Well, we'll do the rest of them. So this one, we want to determine the final velocity of the roller coaster, assuming a 10% loss to friction. Let's just fill in what we know so far. I see here I'm not moving. I'm at the top of a hill. That's EG. And I have to fill in my system. I keep forgetting to do this first. I need to do it. Cart, floor, earth. That's pretty much it. at the bottom here, I am moving, but I also have friction. And so let me just put like 3 here and then 1 here. They give me some information that I normally don't get, is that 10% is lost to friction. And so I get like this EG is equal to EK plus EDIS. And the question is, how do I go about solving this? I know EG is MGH, and I know EK is 1/2 MV squared, but I don't have an equation for EDIS. EDIS is just kind of EDIS. Well, I have to kind of use the problem I've been given here. And so the problem is that, essentially, that 10% of my entire energy is lost to friction. Conservation of energy says this is all of my energy, and this is also all of my energy. It's all the same energy pool we're working with. So this plus this is MGH, or this is just 10% of this. So I can rewrite this as MGH is equal to 1/2 MV squared plus 0.1 MGH. This represents 10% of MGH. And at this point, I could start solving it, but I run into another problem. I don't have mass. How do I deal with no mass? Well, it turns out a lot of energy problems. If you need the actual energy, you need the mass. Almost all of your energy problems involve mass in it. Springs don't, but a lot of times mass pops up anyways. What's interesting is if I just need the speed, all the masses seem to cancel. And so I have GH, which would be 10 times the height, 5, equal to 1/2. I'm solving for V squared, plus 0.1 times 10 times 5. And let me calculate. After calculating it, I skipped algebra there, but I got 9.5 meters per second. So that's what you would get. And I think this is a very interesting relationship, is understanding a lot of times mass can be canceled out. If you need the actual joules amount, you probably need mass, but if you need like height or velocity, you may not need it. What this implies is this cart could be like 100 times more massive, but assuming the friction loss is like the same amount, which it probably would be, then you're going to get the same speed going down. And that kind of matches with projectile motion. Not that this is projectile motion, but all right, last problem. I'm going to try to go quickly so we don't have to have a huge amount of time on here. I'm going to let you guys try to solve this one. Note the railgun is outside of the system. So, I'm going to put like moon as my system, moon, capsule, and that might be it. So, good luck. All right, so this is my setup so far. The railgun's outside my system. If you remember from the previous videos, we call that work. And that's what we're going to be trying to figure out, is how much work is really needed to send this capsule into the space. And now we're around the moon, and we're at a certain surface. And actually, I want to solve this so that I can just see how these numbers are going to play out. The capsule's 10,000 kilograms. The velocity is 1,700 meters per second. That's going to be squared. I'm going to plug in for my known values here. They told me the moon's gravitational field strength is 1.6, and it is 100 kilometers above the moon's surface. Now, this is fine that's above the moon's surface because they're telling me that it is just 1.6 at that moment, so that's fine. And let's see, 100 times, I'll just put 100,000. And I'm going to plug these numbers in. Let's see what we end up getting. So this is the energy breakdown I get. If I add these guys up, I will end up getting a bigger number. But my question is, so I have these two split up as a function. And the question is like, man, these are both really big numbers. How much bigger is this one really from this one? So kind of think about it. Think about how you would want to draw these boxes where I'm trying to get at. So try to rearrange them, see what you... All right, so this is the actual final answer. And it's not that much bigger than this number. This was the kinetic energy needed for this capsule to orbit the moon with that specific orbital speed. Because it's 1,700 squared, that's a big number there. Yeah, and I think this will confuse kids. Whenever you deal with gravity stuff, you're dealing with these giant numbers. And times 10 to the 10 versus times 10 to the 9, this is like a tenth of this, essentially. And since their magnitudes, their front numbers here are about the same, it's going to be about 10%. So if I were really drawing this correctly, I'd probably want to make this column over here like really small like that if I want to be really accurate with the relative sizes. All right, that's going to be it for this video. I'll probably make one more for the typers part.